Hey, Chem 30. So a nice short lesson for today of how to use oxidation numbers to actually identify if it's a redox reaction you're looking at or not. So oxidation numbers can be used to determine if a reaction is a redox reaction or not. If the oxidation state of an atom or ion changes, then oxidation or reduction is occurring and it is a redox reaction. So we just take a look at all the different elements and atoms in the reaction. And if for an element the oxidation number changes, then we know that it's redox, that an oxidation or reduction is happening. Now, there's always going to be one element that's going up in oxidation number and another one that's going down. Because in order for something to actually end up getting oxidized, right, the number going up, then something else has to be reduced. The oxidation number has to go down or become more negative. And this is just simply because you cannot give without somebody being there to take, right? You have to have both. You have to have the losing and the gaining of electrons, both sides of the coin. Okay, so how we do this is we basically just take a look at all the different atoms in the elements and we assign oxidation numbers. And then if we take a look at the oxidation numbers and it's changing for an element, then we know from that that redox is taking place, that it's a redox reaction. If that's not happening, okay, so in other words, the oxidation numbers of stuff is not changing, then we know it's not a redox reaction. So let's take a look and work through this and kind of show how it would be. Now, when I go through this process, I don't care about the balancing coefficients. It doesn't matter. They're there, okay, but they don't actually have any bearing in this work. We're just taking a look for carbon, hydrogen, and oxygen. Does the oxidation number change or not? So if I take a look at carbon, hydrogen, let's start with. I have positive 1 for hydrogen, so I have positive 10 in total from hydrogens, which means I have negative 10 for carbons in total. So I have to divide that by 4, which means I have negative 10 over 4, or simplified, negative 5 over 2 as an oxidation number. O2 is an element, so it's going to be straight up 0 for the oxidation number. In CO2, I have negative 2 for oxygen times 2 is negative 4, which means carbon will be positive 4. I only have 1, so that's positive 4. Something's changing. I have negative 5 over 2 changing to positive 4. So carbon itself is actually going through some oxidation here, right, as an atom. It is losing electrons throughout this reaction. And then if I take a look at oxygen, I can actually tell that O2 is going through reduction because it went from 0 to negative 2. I can finish this up with positive 1 for hydrogen, negative 2 for oxygen. And yes, I know that this is a redox reaction. So in other words, electrons were transferred. I had oxidation and reduction taking place. Wow, the writing is not working. Okay, let's take a look at photosynthesis now. So the last one was combustion, right? Now we'll look at photosynthesis. And those of you who have taken some biology know that this is going to be redox because you have all the electron transport chain stuff going on. I don't remember it, to be honest. It's been a long time, but you got the light dependent and light independent reactions, and I know that there's electrons involved throughout that. So for carbon, I got positive 4 matching the negative 4, so I have positive 4 on carbon here because this comes out to 0. Oxygen, negative 2, hydrogen, positive 1. I'm done with that one. This is kind of a neat one. Negative 2 times 11 is negative 22. Hydrogen is positive 1 times 22 is positive 22. So that means carbon's at 0 here for an oxidation number. And then finally for oxygen, I have 0 again. So if you take a look, oxygen went from negative 2, let's see if I can draw a decent line, negative 2 to 0, right? So this actually ended up getting oxidized because it became more positive. And then if I take a look at carbon, it went from positive 4 to 0, so it was essentially reduced. Now, I'm not being very specific with my language, but right now I'm just talking about the individual atoms and the fact that they went from negative 2 to 0, so that went through oxidation, and then for carbon, positive 4 to 0, so it became more negative, so that's reduction. All right, and the last one, I have silver as an ion is positive 1. Oxygen is -2. So that means nitrogen is going to have to be +5 to make that work, right? -6, +1. So this is +5. For HCl, I got -1 and +1. For AgCl, I have +1 and -1. For HNO3, I have -2 here, so -6. Hydrogen is +1, +1. So nitrogen has to be +5. So now if I take a look, N is +5, +5, silver +1, +1, O -2, -2, Cl -1, -1. Nothing changed. Everything remained the same. So this is not a redox reaction. In other words, no electrons actually transferred at all. For photosynthesis, I didn't write it beside, but yes, it is a redox reaction. So at the end of the day, the following reactions will always be redox. I'm always going to have electrons being transferred or moving from one thing to another. Combustion, cellular respiration, we already know how similar these reactions are from enthalpy. I mean, the only difference, right, is that combustion makes CO2 gas. Wow, that was just ugly, ugly writing. CO2 gas. Well, cellular respiration, because it's a slower process, what am I, back up this truck. Combustion makes H2O gas. It does make CO2 gas as well, but I zoned out and I meant to say water. Well, cellular respiration makes H2O liquid instead because that reaction is happening much slower. So as a result, the water isn't vapor, it's liquid instead. And as a result, these two have different energy changes, which you learn about all in the enthalpy chapter. Photosynthesis, which is essentially the reverse of cellular respiration, is also redox. When you look at single replacement, that's going to be a redox reaction all the time. Formation reactions are generally going to be redox reactions. In fact, I can say pretty much always. I can't think of any examples that wouldn't be. And in the same way, if I have decomposition, this is also going to be a redox reaction. And we're sticking with the Chem 30 definitions for this, and that formation is from the elements, right? So from the elements. And then when I have decomposition, this is going to be to the elements. The only thing I can think of is if we have atoms that are so perfectly the same electronegativities, but we're not going to get into that. So we can come up with these general rules that in Chem 30 formation is always going to be redox as well as decomposition. Well, double replacement is not a redox reaction ever. So this includes things like precipitate reactions, right? So if I have two aqueous compounds reacting to make a precipitate, then that is not going to be a redox reaction. Also, neutralization reactions, that's a double replacement. That also will not be a redox reaction. So no electron transfer is taking place in those reactions at all. All right, that is it. You got a worksheet to try out for this, so give that a go, see how it is, and have a good rest of your day.